Okay, here we are where we left off last time. Previously, we learned how the time series generator works. And what we're going to do is we'll go ahead and make sure we create a generator object for us to train off of. And what we want to do is make sure that we get basically a full cycle or full seasonality within one length of one of our batches. So we know that there's about 500 points between 0 and 50. And we can see here that a cycle goes from about 0 to maybe a little greater than 5. So if we think about this, we probably want at least somewhere between 50 and 100 points within our batches. So let's go ahead and just say 50 here. So we'll say 50 and we'll send one batch at a time. We'll go ahead and create this generator, and now it's time to create our model. We will say from TensorFlow .keras.models import sequential. And then we'll say from TensorFlow .keras.layers import, and we'll be using a dense layer, and we'll begin by using a simple RNN layer, and then we'll expand this to an LSTM. Okay, so the last thing we need to define is how many features are we actually training off of. And in our case, we just have one feature input, which is X, trying to predict Y. So the number of features is just 1. And then to begin creating our model, we'll say model is equal to sequential, and then we'll say model.add, and we'll add in a simple RNN. And the simple RNN has a lot of parameter calls that you can pass in, but here we'll just focus on the basics, such as the number of units, how many neurons are here, and then the other important one is the input shape. So you actually can't see here, but we have to define what the actual input shape, and luckily that's actually pretty easy, given that we've already defined the generator. So the actual number of neurons, you want it somehow related to the length of the batches. Since I'm passing in 50, let's go ahead and just choose 50 neurons here. And then the other thing I need to put in here is the input shape. So we'll say input shape is equal to, and we'll say length by number of features. And then after this, we want our final prediction to just be a single number. So we'll say that all goes into a single dense output, and then we will compile this. And this is essentially a continuous value or continuous label. So we'll say optimizer is equal to atom, but more importantly, our loss function is just going to be mean squared error, just as we always do for continuous values. Then go ahead and run that, and then your model should be created, and you can confirm a summary error model by saying model.summary, and here we can see the different layers. So what we're going to do is instead of saying model.fit, since we're using a generator, we say model.fit to generator. And then we pass in the generator that we just created, and then we choose a specific number of epochs. And later on in this lecture, we'll show you how to actually implement early stopping by creating an early stopping generator based off your validation set. But for this, I'll go ahead and just train this for, let's say, 5 epochs. Run this. And keep in mind, recurrent neural networks, they definitely take a lot longer to train than typical artificial neural networks. So expect this to take quite a bit longer, even if we're only training for 5 epochs. I'm going to fast forward in time until this is done training. All right, I just fast forward in time, and now I fit in 5 epochs. Let's go ahead and evaluate our losses. We can do this by simply saying losses is equal to pd.dataframe model history.history. And then let's plot these out. And we can see here we're definitely reducing on the first couple of epochs, and it almost looks like we were increasing. So later on we'll see how we can compare this to validation data and probably institute an early stopping mechanism. But let's go ahead and evaluate on our test data. So to do this, I'm going to show you our logic here before we write it into a for loop. So let's imagine what is the first batch I should be passing in to my model to predict something on the test set. Well, that should be coming from my scaled training data all the way from minus length to the end. Essentially, we're going to take the last 25 points from our training set to predict 1 point into the future, which is the very first point in our test set. So I have my first evaluation batch, which I can take a look at if I want, and I can see it here. And essentially what I need to do is, in order to pass this into the model, I actually need to reshape it to the shape the model expects, which to generalize it will be 1 by length by n number of features. And then we'll say first eval batch is equal to the reshaping of it. And now the model should be able to predict this. We'll say model predict 1 point into the future given the last 25 points in the training data. So it's model.predict first eval batch. We run that and we get back our prediction. Now we should recall that we are predicting scaled predictions so far. So I can compare this to my scaled test point, and this is the very first point here in my scaled test, and we can see we're actually doing pretty good. I predicted 0.948, and my first scaled test point is 0.949. So definitely not bad. What we need to do is we need to put this logic now in a for loop to keep moving essentially 25 points. And as we keep predicting, we'll add an additional predicted point until we're essentially predicting or forecasting off predictions. So what I will do is essentially create all this logic that we did here in these 4 cells and put it into a for loop. So what I want to do is say my test predictions is an empty list. And then I have my first evaluation batch equal to that scaled training data, where I have minus length all the way to the end. And then my current batch that essentially I'm currently using will start off as my first evaluation batch reshaped to 1 length and features. And then what I need to do is essentially create a for loop that keeps appending this. But something I want to show you is if I run this, notice that my first evaluation batch is right here, but the shape of my current batch, essentially after I reshape this, looks like this. Notice the extra arrays. And what I need to be doing is I need to keep appending all this data except for that first original point, because I'm replacing that with my new predicted point at the end, essentially moving 1 step forward. So what I'm going to be doing, and this is where the code gets a little complex because it's a lot of NumPy indexing, but I will be running this command. I will be saying np append current batch, and this is where the indexing gets really complicated, so watch carefully. We'll pass in the following commands, essentially saying, based off the dimensions, grab everything in the first dimension, everything in this last dimension, but in the actual dimension that's holding the data, go from index 1 all the way to the end, essentially dropping that first original point because we don't need it anymore since we're not actually using it. And so I will then put in my predicted point. So let's imagine we have some predicted value. This is just to make it obvious. Let's say my predicted value is 99. Notice I have 3 braces since that's going to be the same format that predictions are in. If we take a look here, notice I have 2 braces and then my number. So what's going to happen is I need it to have an extra set of brackets here so I can use np append. So if I say here 99 along axis is equal to 1, so let's say this is my predicted value, I'm passing in it raw here, go ahead and run this, and let's compare this now from our current batch to our first evaluation batch. So our first evaluation batch goes 8.37, 7.98. What I want in my current batch as I keep moving is go ahead and drop the very first point, and now I'm at 7.98. So notice I dropped 8.37 and moved straight here. And after dropping that, go ahead and add our predicted point to the end. So instead of ending at 9.25, if we scroll down here, we go from 9.25 to that 99 that I inserted. So a lot of this essentially isn't that complicated. The complex part is actually implementing it with NumPy. So all this code is doing is it's saying, go ahead and move that current batch along by 1 time step, which we talked about in the theory lectures, that we just keep moving this forward and forward. The complex part is because we're dealing with so many dimensions, the calls are actually kind of a little weird. You're only grabbing from 1 here all the way to the end in the middle dimension, and then you're going to have to set the predicted value with a set amount of dimensions, because it's technically 3-dimensional, because it's a tensor, and then we append along axis equal to 1 because we're appending along the information axis here. Okay, so I know that's a little bit complicated, but I just wanted to kind of walk through that logic, and then we're going to essentially make a for loop out of that logic. So I'm going to copy and paste what I have here, because this actually doesn't change. The initiation of the logic doesn't change. All we do then is we say for I in range, and we're going to do this for the entire test set. We'll say for length of test set, go ahead and say my current prediction based off the current batch is model.predict current batch, and I'm going to index an item off of that to be my current prediction, and then I will take my test predictions, which remember starts off as an empty list, and I simply append my current prediction. And what I have to do is then move my current batch forward 1 time step. And that's where we do this kind of complicated logic here. So I will copy this and say, I'm going to update my current batch is equal to np append current batch. This stays the same, except what I'm inserting is not some arbitrary value of 99. Instead, it's going to be, notice I'm deleting the 99 and the braces, and say my current prediction. So keep a really careful eye here on the braces. In fact, I would highly recommend you just copy and paste this from our notes. So what I'm doing here, just to walk you through it, is I have an empty list for my test predictions. I grab my first evaluation batch, which is the last, essentially in our case, 25 points of the training batch, and then I reshape it to make sure my model can accept it based off the length and number of features. And then I set that to my current batch. I do my very first prediction. That's my current prediction right here. And then what I'm going to do is I say, okay, go ahead and grab that current prediction and append it to that list. But now, to keep predicting into the future, I have to move my current batch 1 step forward, which is essentially what this does, is it gets rid of that first item and instead replaces that by adding the current prediction all the way to the very end. And now if I run this for loop, what's going to happen is I should essentially get now pure test predictions by the end. So this is now my predictions for the entire test range. Okay, and now I'm going to essentially be comparing that to my scaled test data, and we'll hopefully see it work well. Remember that this is scaled, so let's go ahead and inverse that transformation. We can do this easily by saying my true predictions are equal to scalar dot inverse transform these test predictions that we just created. And now my true predictions are in the right scale. Okay, so once that's done, all I need to do is figure out ways to compare this. Recall that I still have my test data frame with that test set. So what I can do is say, add in a column called predictions and set that equal to true predictions. Keep in mind, you may get a warning about something saying a value is trying to be set on a copy of a slice. It's essentially warning you, hey, you're editing permanently your current test data frame. So you can go ahead and ignore that warning. That's actually the behavior we want. It's essentially pandas telling you, hey, you're editing this permanently by running this, but that's exactly what we want. I want something that looks like this. And then once that's done, let's go ahead and plot it out and see how we did. We'll say test.plot, and we can expand on this figure size a little bit, just so it's clear. And we'll say, whoops, fig size is equal to 12 by 8. Go ahead and run that, and you should see something that looks like this. Notice our predictions are definitely not perfect, but it's really interesting to see that our model is actually able to start to mimic the behavior of a sine wave. However, you'll notice that as we're predicting further and further into the future, our values are getting further and further off, which makes sense because we're predicting off predictions. So this very first point should be the most accurate because we're using real data, those last 25 training points, to predict my first point into the test set. And then as I move to the next point, now I'm using 24 points in the training data plus my predicted point in the test range to predict a new point. And then I'm using 2 predictions to predict the next point, then 3 plus the old ones, until all the way to the end where I'm using essentially 24 training points, or excuse me, 24 points in my test range that I predicted, plus 1 original training data to predict the last one. So it kind of makes sense that we're getting further and further off because we're doing essentially true forecasting at the very end. But our behavior is looking pretty good. This is a pretty smooth prediction line, and it looks like a sine wave. So coming up next, we're going to see if we can improve on this by using an LSTM unit. I'll see you there.